Welcome back to my YouTube channel. In this video, I'm going to show you another chapter series for my online tuition video. This video is for SPM Form 5, Chapter 3, called Electromagnetism. Now, to start off with, I'm going to talk about the chapter itself, because over here the name suggests electromagnetism. What does it mean by that? In this chapter, it's a continuation from what we have learned, where we study the effect of the movement of the electron. In the previous chapter, we know that whenever there's an electron flow, that would be actually called current. Current flow in the opposite direction to where the electron moves. When the electron moves from left to right, therefore current from right to left. So that's current, electron and current. Okay. So in this chapter, we study the effect of the movement. Whenever electron move, whether it is translational or it is rotational. Okay. Whenever electron move, what happens? You are going to have magnetic field. So whenever you have a soft core ion, soft core ion is actually a ball and nut here. Whenever you have a soft core ion and copper coil with current moving around it, coils around it, and then you will get electromagnet. And this electromagnet will have electromagnetic field and ferromagnetic or the ferromagnetic material will be attracted to it. So this effect is caused by the movement of electron, or current moves in the coil concentrated by the soft core ion, powered by direct current. Now I know there are quite lots of terminologies happened in the past. You may pause this video. That's good about YouTube. You may pause this video and rewind to the previous minutes that you have missed. Alright, okay? So you need to get the concept right, because whenever there's a movement of electron, then you will get magnetic field. Movement of electron, you get magnetic field. Okay, and magnetic field is the region where you have magnetic force. So here you expect to have magnetic field around this area. Okay, they are going to have magnetic field. This is the magnetic field where you have magnetic force attract all the ferromagnetic material. So to start off with, just like in your reference, I hope your reference is video, because we'll go through it according to your reference. So we start with material, the understanding of material. Okay, there are actually three categories. You get to learn all these three categories. From conductor in chapter 2, conductor, where you have material that allow electron to flow, we call it conductor. To semiconductor, next chapter, where you get to learn the electron band and valence band, the valence band and conductor band. Okay, and insulator is actually we don't have that in this syllabus SPM, but you know that the insulator is the opposite of conductor, where the material that does not conduct electron. Okay, does not conduct electron, or the valence band and conduction band is very huge. Okay, or no electron flow allowed. A rough way of doing, or another way is we talk about the band gap. Okay, the huge band gap. Well, you get to learn about these terminologies in the next chapter. Like for example, glass, okay, rubber. Okay, those are considered as insulator. The best one would be the wood. Okay, those are insulator. So we will go back into, we will come back into semiconductor in the next chapter. So as for this chapter, we talk about conductor. Previous chapter we talk about conductor, flow of electron. And the effect of the flow of electron, you get electromagnetic field. Where you need to understand that in conductor there are two types of conductor. One is a ferromagnetic material. Another type is called the conductor with non-magnetic material. So for ferromagnetic, is the famous tree. If you have your periodic table, as you have learned in chemistry, you have ferrum, cobalt, nickel, the 3D orbital. Okay, in periodic table. Okay, now these are the elements with an unpaired electron. Okay, because the electron rotate at its own axis, so you get a net magnetic domain. Okay, you doesn't need to know that, but as long as you know the electron move, it is not translational movement. In previous chapter, we talked about electron move from one end to another end. You get magnetic field. Here, conductor, the electron valence in the outermost orbit rotate at its own axis, then it's also some sort of movement, and that kind of movement would contribute towards a magnetic moment where you can get the overall magnetic field, or defined as ferromagnetic material. For non-magnetic, however, but they are conductor, I'll give you one example that is called the copper. Copper is a conductor, but it's non-magnetic material. Another example, you may go to a book, is called the pure aluminum. It conducts electricity, but it's not magnetic. You don't confuse yourself, because there are some aluminum bar, but the surface has been oxidized. Okay, so when you have oxide react with aluminum oxide, then it no longer conducts electron. It could be actually a semiconductor, or perhaps insulator. It's not insulator, but maybe it's a semiconductor. Okay, for non-magnetic conductor, aluminum element, the pure aluminum, it conducts electricity. Okay, then if you have this in line, then next you get to understand the North Pole and South Pole. You may pause this video and go back to the previous previous page on magnetic field. Okay, so here around this area vicinity, you are going to have magnetic field. It's a region. I'm going to do it here instead, better. This region around here, this region is they will have experience magnetic force. Symbol, I would say F force, B magnetic force, and this is called magnetic field. Magnetic field is an area where the magnetic material, the ferromaterial experience magnetic force. Okay, so this is what you meant by that, and I think it came out in one of these objective question. Okay, so for the first part of this video, it's all about Faraday law. Faraday law, that would be what? That would be, it says, when the magnetic field is strong, in order to get a strong magnetic field, what would you do? You need to have a lot of coil, and you increase the current. Because you increase the current, meaning more electron flows through it, then the magnetic force will be strong. Okay, that's basically what the Faraday law is all about. Then next, from your reference text, you get to know the direction. Okay, the direction or the arrangement. Okay, they will normally comes out in your objective question. If you have a conductor in a U-shaped wire where current flow up from the left comes out over the right and it passes through a paper. I have a video. Made to trace the magnetic hard magnet. We call it a hard magnet because ferroelectromagnet is actually a soft magnet. So I have a video made to trace the hard magnet appear in an iPhone. So you may want to look at it, how to trace it. But this is a conventional method, like what you have seen from your textbook. So if you look from a top view, current flow through it, what happened is around this area, and you sprinkle with metal fouling. I think I'm going to erase off because this should be covered by the paper. You can't see that. Okay, so it's more realistic now. Okay. This point. Okay, what do you get? This is where we apply your Maxwell screw rule or right hand grip rule. Okay, by making use of Maxwell, I think the best way is called the Maxwell screw rule, or you call the right hand grip rule. Right hand grip rule, or you call it corkscrew rule. So what happened by placing a right hand thumbs up? What happened? All your four fingers will close around this wire, so will be in, right? The same goes to here. Current go down, your thumb points downwards, and then your finger will close around here. Okay, around here, around here, around here. Okay, thumbs up. So what happened? Thumbs up, all your fingers will close according to counterclockwise. Whereas when thumbs down, what happened? Your finger will close, grips around, and it will form a clockwise rotation. Okay, I'll try to give you an illustration. Your thumbs down. Wow, it's really hard to draw it. Then all four fingers will actually close, right? It will close 2, 3, 4. Okay, your thumbs. Okay, this is your hand. I know I'm not very good at drawing, but I try my best to draw it because the thumbs follow the direction of the current. Means current flow from positive to negative. Positive up, down. So here, up, point up, then it will close in clockwise. This is anti-clockwise. Whereas thumbs down, follow current down, it will be a clockwise direction. Okay. The direction of it, it's grips rule, Maxwell grips rule. Okay, the first part. If you want to trace it, it will be the left one here, you have dotted line. Those dotted line represents ion fouling. Okay, the left. So what you get, a dot. Why is it a dot? Because you analogy this as an arrow. When an arrow shoots up, what would you get? When an arrow, this is current up, so an arrow shoots up. This is an arrow, right? Towards your eye, what do you see? You see a dot. That's why in your diagram it's a dot. So right hand grips rule or Maxwell rule, what do you see? The direction would be anti-clockwise. That would be this, go down, upwards. Okay? You are supposed to know how to draw this because it will normally comes out. Now here, what happened? Your eye will see arrow going into it, right? Your arrow go down. You will see the tail, right? You will see this tail. So what happened? To represent that, it will be a cross. Cross meaning going into the surface. Those are the pattern for ion fouling. Right hand grips rule, going into it. That would be downwards. Okay? Go around it. Okay? When it's too close to each other, what happened? It enhances it. It becomes bigger. Okay? The next thing you need to learn, or you should know by now, would be called the solenoid. That would be the next term. Okay, solenoid. What's a solenoid? Solenoid is like what you have seen in my previous page. Instead of winding together, what happens is you wind them around. Okay. Now, I think the best would be on a piece of paper. I mean a plane, because you are about to trace. You are about to trace the magnetic field. Okay. Okay, on the plane. So what happened? You have a wire goes in from below, comes up, goes into it, then curl around, and then comes up, comes out, and then goes out. Okay, so you can have quite a few numbers of it. So what happened in the event that currents go in, goes around it, so go up, down, and comes up from here, and then goes out from here. So whenever current goes around, solenoid is actually an arrangement of wire in a coil form, right? I think I showed you an actual model in the previous page, the opening of this chapter. So what happened? Again, right hand grips rule or Maxwell's screw rule. What happened? You get north pole from the left, south pole over the right. How you do it? 4 fingers, because you follow the current. Now it's not the thumb, now it's all your 4 fingers. 1, 2, 3, 4 fingers, and then your thumb. Okay, you curl around this wire. You curl around it. So what happened? Your thumb point towards the north. That's why this is how you determine the North Pole. Okay, always about right-hand Gibbs rule. It's about where the direction of your magnetic field. Okay, so you may read through your reference tags. Okay, important part is this one, the sign, dot and cross based on the arrow, and the arrow direction based on where the current flow. Okay, and the ability to identify where is the north and south pole for solenoid. It's all about right-hand Gibbs rule. All you need to do is to look at the wire arrangement, follow it. Where's the current? Where's the positive? Obviously this is positive, this is negative. Current flow up, down, and then right-hand Gibbs rule to determine where's the north pole. You may want to pause this video, go through the exercise in your reference or in your exercise, chapter by chapter exercise. You need to try maybe about 10 to 15 questions, objective questions, to see if you follow this rule, because it's not much of calculation, not much theory, it's about understanding of it. Okay? Or else, let me put down the real deal. During the beginning of this chapter, or summary, okay, we talk about, actually it's called electromagnet. Okay, what is electromagnet? Electromagnet is this, the one I show here. This is an electromagnet, meaning you have electron movement and you become a magnet. Okay, that is actually an electromagnet. Electromagnet is a temporary magnet. Temporary magnet. You pass through a current, direct current, it has a direct current, then you get a magnet. Okay? I mean, it acts as a magnet when direct current pass through and it will lose its magnetic field when the current it's switch off. Okay, so that's when direct current pass through, you get magnet, and it will lose its magnetic field when it's switch off. Okay, then about the strength. Okay, we are going to mention previously the Faraday law. Okay. Okay, the Faraday law is all about the strength, how strong. There's a set of experiment in your reference. How I'm going to test the strength? I mean, they calculate the amount of paper clip. Okay, what are the things that affect the strength? Okay, first, your current, direct current. If you increase the current, then the magnetic field strength will be increased. Or number of coil. If you want to lift 500 grams, ideally you need about at least 1,000 coil. So number of coil affects the strength. Okay, and then option. I mean, it's something you need to know. It has to be a soft iron core, so that it helps focus or you were able to gather all the magnetic field over the end of the tip. Okay, let's say a solenoid. Okay, arrangement of solenoid. Why soft core iron? Okay, why soft core iron? Because, first point, why do you use soft core iron? Because it is, first of all, it's a ferromagnetic conductor. It will be easily magnetized. When current passes through, direct current pass through. I mean, in order for this electromagnet to work, you need to use direct current only. Okay, you don't expect alternate current would work. Okay, now you just get to know what is direct current. Just direct current meaning just like from a battery. Okay, what else? What the benefit of using soft core iron? Easily magnetized. It will be able to concentrate. I put that into a point form. You may jot down your own notes. Concentrate the field line, the magnetic field line. Therefore, you give a strong, so that you get a stronger magnet. Okay, concentrate it so you get stronger magnet. Okay, the last point, very crucial, because you talk about electromagnet, it will lose all magnetic field. When the direct current is switched off. Okay, that's why you use soft core iron. Okay, you know the importance of it if you have gone through some at least 15 questions objective. They will talk about soft core iron. You may want to compare a soft core with a steel. What happens if you use a steel versus soft core? Okay, if you have sufficient amount of current, direct current, high enough current, because it's not easy to magnetize like steel, you need to have strong magnet, or perhaps a small amount of steel. Let's say a nail with small amount of carbon onto it, a steel. What happens if you were to have a magnetic coil around a nail, and then you coil around it, lots of coil, and subjected to huge potential difference or direct current? What happens for steel? It becomes permanent magnet. This is something that you need to know. When current passes through it and it becomes permanent magnet, meaning when you disconnect it, what happens? This steel will be still a magnet. You will still get a magnetic field. You will still get magnet. So it's useless now, because you can't use it to attract and engage and disengage of your door. Let's say, for example, you can't work as a lock. You know, in some security door, they use soft core instead of steel, because when you pass through current, then you will lock it. When you want to unlock the door, all you need to do is cut off the current, then the door will be switched on. I mean, you're able to open up the door. So you do not use steel. It is still ferrum, but still you have ferrum plus copper at least, or some maybe chromium. Soft core, it's about ferrum. Okay. Soft core is important, something that you need to know. One thing is it will lose all magnetic field when it switch off the current, and easily magnetize, and it concentrates the field line. Okay. Before I end this video, I would personally advise you to read through the application for electromagnet. Like for a speaker, how does it work? It's available in your reference text. You should read it in a week time. After you watch one video, you should spend a week to read your reference and also do the exercise, 8 to 10 questions. Speaker, important one. Maybe electric bell. Or in some book they will have a relay switch. Okay. We'll talk about relay switch in next chapter, but it's good to find out how does a relay switch do with electromagnet. Okay, that's all from me. I hope you if you're first time watching this video, kindly subscribe to my channel for more upcoming video. And if you are continuing viewer, those thumbs up button either in YouTube channel or maybe in my Facebook page, it helps other people too, and it helps this video to grow. That's all from me. Thank you for watching my video.